I am Michael Parizh, and I represent GE Global Research. Before working for GE Global Research, I was working for about 15 years for magnets for Philips. So what I'll try to do is to be as non-partial as possible. I will show the picture of the industry, and I will show how wide is our field of MRI. Contrary to Tom, I will avoid any formulae. So we will talk about magnets for magnetic resonance imaging. How I should turn this button? This. Okay. I will talk about magnets for magnetic resonance imaging, and because the majority of MRI magnets are built using superconducting technology, we may say superconductivity serves people. MRI uses strong magnetic field to produce images. All parts of human body, from head, brain, spine, extremities, can be done using MRI. Patients of all ages, all genders, both genders, can be imaged using MRI from fetus to pregnant woman to mature adult. Okay, so what we will talk is about MRI marketplace, superconductivity, and MRI. And if we have time, we will talk about some aspects of the MRI magnet design. What customer needs to know. MRI marketplace, well, installed base, types of MRI magnets, and cost. Well, magnet is single most expensive component of the system. Here I will use many numbers about installed base. These numbers are very often my best guesses. I'll try to be, as I say, as impartial as possible, and forgive me if you know better information. This information is based on all literature searches, discussions with marketing people, with my colleagues from different organizations. So, annual production, about 4,000 systems. It's $10 billion industry. Superconducting magnets represent more than 3/4 of the marketplace, about 80 million examinations per year. As we see from this chart, if we are talking about installed base, United States and Japan use about half of world MRI. In these countries, about 80% of new MRI scanners are installed in existing facilities, typically replaced by higher field and better patient comfort systems. At the same time, we see a shift in the dynamics in the MRI market. Today, about a third of new MRI installations are in developing countries like China, India, Brazil, and there 60% of new scanners are installed at new facilities that this didn't exist before. Definitely, we as industry are trying to reflect the change in dynamics. Yes. For future discussion, let me remind the units of magnetic field. I'm sorry if it's too simple for some. So two units are used, Tesla and Gauss, and 1 Tesla is equal to 10,000 Gauss. Central field is typically measured or reported in Tesla, so standard commercial 1.5 Tesla MRI is about 50,000 Earth magnetic field. At the same time, stray field limit 5 Gauss is typically expressed in Gauss, and this is 15 times of Earth's magnetic field. Oops. Types of MRI magnets. There are 3 major types of MRI magnets. Permanent magnets, permanent systems where magnetic field is generated by strong permanent magnets, typically neodymium, ferron, boron. Resistive magnets, where copper in superconducting in the wire produces field, and obviously we know that there are significant heat losses in this conductor. The principle of operation of superconducting magnets is about the same, but there is no resistance, so no heat losses. However, these magnets must operate at very low temperature. Oops. How to return back one slide? Yes. Okay. Early MRI systems used resistive magnets. Today, resistive magnets represent less than 5% of the installed base. Their advantages are a low installation cost, ability to turn off magnetic field, and what we see here, open access. There are significant disadvantages. They are limited to low field, typically less than 0.6 Tesla, in reality even less than 0.6 Tesla. So high field, high-end images are not possible. There is a drifting magnetic field, so uniformity is not as good. They are heavy, expensive, they require water cooling, and the power bill is huge. For example, if all MRI in the United States would use resistive magnets, 5% of the electric power produced in the United States will go to MRI. There are about 2,500 resistive systems installed worldwide. More than half of them use one of those two systems, Siemens and Philips is discontinued now. Phonar from Melville, New York, is the only company that is solely dedicated to resistive magnets. About 400 Phonar magnets were produced. And this 0.6 Tesla Phonar upright is a unique system. It allows making images in a different patient position, including knee and spine image while bearing weight. The power bill for this system uses about 1/4 megawatt power, so power bill is about $100 per scan. Permanent magnets, it's about 15 to 20% of the installed base. And their advantages are, well, no power used, easy to maintain. Typically what we see, open access. Disadvantages are, once again, it's low field, uniformity, and especially field drift during image is not good for high-end images, very vulnerable to patient motion. Hitachi dominates the marketplace. About 5,000 Hitachi systems were installed worldwide, including 2,000 in the United States. And if we count in the number of units, then Hitachi occupies up to 15% of the US market. And Hitachi mainly delivers those two systems, 0.3 Tesla Iris and 0.4 Tesla Aperto. As I already said, permanent magnet systems use rare metal neodymium, and 90% of neodymium is excavated in China. Recently, we see a huge increase in neodymium cost, which could make permanent magnet systems commercially uncompetitive. In 2009, cost of neodymium was $6 per kilo. In 2011, it jumped up to $450 per kilo. Today, it resided at about $100 to $120 per kilo, which is a factor of 25 increase versus what it was 5 years ago. The most advanced are superconducting systems, and they are about 3/4 of the marketplace. The highest magnetic field, the highest temporal stability and uniformity, highest signal-to-noise ratio, the only configuration for thin slices, shortest scan time, the highest throughput. As a magnet designer, I should say the lowest stray field and the most compact design. Disadvantages, the highest purchase price, expensive service contract, and those magnets may quench or lose magnetic field, which is interruption of service that is typically lasts a day or two. 3 Tesla magnets represent about 20 to 25% of new superconducting MRI. And here I showed the most advanced 3 Tesla wide bore, 70 centimeter bore patient bore systems from different vendors. This from GE, Philips. This is my baby, by the way. Siemens and Toshiba. Oops. Yes, MRI went quite a distance from where should I point it? Okay. Quite a distance from maturity. This is the first MRI pattern that I found. On the right, we see newer superconducting MRI, which offer excellent image quality, great patient comfort, and great industrial design. So let's talk about superconducting magnets. There is a great synergy between superconductivity and MRI. Superconductivity made MRI a commercial reality. Well, 5% of electric power in the United States is not really an option. And also MRI transformed superconductivity from scientific laboratory to everyday use. Too much animation. Okay, let's talk about superconductivity. Certain materials at low temperature exhibit zero resistance to electric current. The temperature at which superconductor loses its superconducting properties and obtains resistance again is called critical temperature. Unfortunately, critical temperature is pretty low. Even for the highest temperature superconductors is less than 100 degrees Kelvin or minus 200 degrees Celsius. Superconductors are very efficient in terms of carrying current. If we compare niobium titanium conductor, the most common superconductor, and copper, copper is a factor of 10 more expensive, is measured in units of per unit current that it could carry. This chart shows just an introduction of the magnet design. The higher is the temperature, the lower is the refrigeration cost. But obviously, the higher is the temperature, the higher there is the material cost. And somewhere here, we have the optimum design. So what we are trying to find is where is the best compromise. Okay, so far niobium titanium is MRI material of choice. This is a mature, very manufacturing-friendly conductor optimized for MRI. It is very mechanically strong. The major application of this alloy is in aviation industry and bridge construction. It's the lowest cost superconducting material, and the disadvantage is, well, it requires operation at liquid helium temperature. This chart shows a comparison of 12-gauge wires that I bought at Home Depot. You see, this 3 millimeter conductor carries only 40 amp current. Niobium titanium wire, half the diameter, can carry 1000 amps. And it contains in small superconducting filaments from hair size embedded in copper matrix. Those are typical configurations of superconducting wires. Those dark dots are niobium titanium filaments. MRI is the largest application of superconductivity. MRI industry uses about 60% of all niobium titanium conductor, and it uses approximately 20% of helium production worldwide. And MRI is one of very few industries where helium is enabling. Luckily, there is a huge advantage in cryogenic technology, which allows a reduction of helium usage by a factor of 4 compared to what it was just 10, 15 years ago. So let's talk about magnetic field. The advantages are obvious, and this is what we learned from the previous presentation. It's a higher image quality that might be crucial for certain abnormalities, especially brain, higher signal to noise and contrast to noise ratios, higher scanning speed, higher throughput. However, there are challenges and disadvantages. Higher cost, in some cases smaller field of view, higher stray field, need stronger gradients, more challenging gradients, stronger power supply, require special scan protocols, and potentially higher patient discomfort that we shouldn't disregard. Okay, in the last decade, the 0.5 Tesla and 1 Tesla magnets practically went out of production. Their marginally lower cost was not sufficient to outweigh advantages of commercial MRI systems. Today, 1.5 Tesla is the working bee of MRI industry. It's about 70% of the installed base and 65–70% of new MRI, superconducting MRI scanners. These systems, 1.5 Tesla is probably the best compromise between multiple conflicting requirements from higher image quality, higher throughput, lower stray field, patient comfort, cost, and so on. 3 Tesla units were introduced early in the last decade. Initially, they suffered from issues like large size, sometimes unreliable operation, high stray field. Today's systems, 3 Tesla is the fastest growing segment in MRI industry. It takes about 10–15% of the installed base and about 20–25% of all new shipments of superconducting scanners. In terms of uniformity and field stability, commercial 3 Tesla systems are similar today to 1.5 Tesla systems. High field magnets, 7 Tesla and higher, are limited to few research clinics and only about 50 units installed worldwide. This chart shows how definitions change. In the 80s, 0.5 Tesla was standard, and 1.5 Tesla and 1 Tesla were considered to be high field systems. Today, 1.5 Tesla and 3 Tesla are standard, and only 7 Tesla and higher are considered to be ultra high field. I would like to have a crystal ball to see where this trend goes. Okay, 7 Tesla whole body magnets. They are typically produced by Agilent Technologies at England plant, and companies like Siemens, General Electric, and Philips integrate them into systems. They offer the highest image quality. Special resolution in human are 0.5 millimeters, even better in animals, because you can center and a higher uniformity zone. Unfortunately, those systems are very heavy, very expensive. The weight is 25 tons or more. They use more than 10 tons of conductor alone, which is more than an order of magnitude more than in the commercial 1.5 Tesla systems. Their stray field is huge, which requires shielding like 400 or more tons of iron, and shielding alone costs $250,000 or more. Bad news. We expect interruption of deliveries in 7 Tesla systems. In March, Agilent announced that they will interrupt production of 7 Tesla systems. They promise, however, that existing orders will be honored. This is absolutely unique and exciting project. This system is under construction at the Neurospin Center in Saclay, France. The center is led by Denis Libihan. The center will include existing 3 Tesla in Bay 1, 7 Tesla system ordered from Agilent Technologies in Bay 2, and 11.7 Tesla magnet will be installed at Bay 3. Please, sometimes I initially thought that this is how the future goes. No, this is where each particular unit is installed. This is a huge system, 5 meters long, 5 meters diameter, stored energy almost 400 megajoules. This system could boil 100 liters of water in an instant if we use all energy. What makes this system unique is, of course, a budget. 200 million euro, including 400 million for the magnet and $7 million for conductor. This is one in the decade project. And we all wish success during installation, which is scheduled 2014, and successful operation. This is production manufacturing of the coil in Alstom plant in Belfort, France. The National Research Council is looking for projects beyond 2020. And they are working with the National High Magnetic Field in Tallahassee, Florida, on a proposal for whole 20 Tesla whole body MRI system. What 20 Tesla offers? This is a comparison of resolution 3 Tesla 1.1 millimeter at 20 Tesla 0.2 millimeters. It's even better in animals. And here we see images taken at 21 Tesla and 9.4 Tesla. The 20 Tesla is done in this 900 megahertz NMR magnet. This photo doesn't show a scale, but this is a 2-meter diameter NMR. Obviously, besides obvious magnet technology challenges, there are many MRI challenges for 20 Tesla system, including scheme death, the electric wave reflection, to say a few. I believe that the decision about construction of this 20 Tesla magnet and the future of this magnet will be done only after successful operation of the 11 Tesla INMAC system. Okay, so now let's talk about shape. There is always a trade-off between the higher quality images that are done in cylindrical magnets and more patient-friendly open systems. The cylindrical magnets represent more than 95% of all superconducting scanners. This is a very mature, well-optimized design that offers the highest uniformity, the highest field, the lowest stray field, and low reasonable operating cost. It has a known but accepted disadvantage. It's a tunnel, typically 60 now to 70 centimeters diameter and about 1.5 meters long, which results that some obese patients don't fit into the tunnel, claustrophobic effect, and some image-guided procedures may not be done in this system. The alternative is an open configuration, which offers better patient comfort at a cost penalty and image quality. There are two open configurations. This configuration, which is called high field open, resembles us resistive magnets in terms of patient comfort. It allows some image-guided procedures. About 800 such systems were produced by Philips, General Electric, and Hitachi, with field ranges from 0.7 Tesla to 1.2 Tesla. However, this system doesn't allow actually direct physician comfort to the patient. In 1995, General Electric introduced MRT, or magnetic resonance therapy unit, where physicians could work within MRI. This was really an operation room inside MRI. Unfortunately, cost of this system was prohibitively expensive, and it precluded widespread of this system. I would like to stress that superconducting magnets may be built with wider access with better access resembling resistive and permanent magnets. But hospitals and patients require higher throughput, higher field, and it results in a different cylindrical shape of the magnet. And a few words about the last application. It's extremity scanners produced by General Electric and Paramet in Italy. Several hundred units, such units were produced. So let me replicate the dominant configuration of commercial scanners. Field 1.5 to 3 Tesla, horizontal bore cylindrical geometry, 60 to 70 centimeters patient bore, niobium titanium conductor that operates at 4 Kelvin, uniformity zone 10 ppm peak to peak in a pretty large ellipsoid up to 50 centimeters diameter, stray field measured from the center of the magnet 4 meters by 2.5 for 1.5 Tesla and 5 by 3 meters for 3 Tesla. Extremely low field decay, less than 0.1% field loss per year if nothing is done. And they have 1,000 to 2,000 liters of liquid helium on board. So now a few words about MRI magnet design. How much do we have? 5 minutes. Okay. Okay. Requirements to MRI magnets, there are very conflicting requirements between higher throughput, higher field, patient comfort, and at the same time cost issues. So MRI commercial magnet design is always a compromise, always. MRI scanners are safe if properly used and maintained. And here I listed some of the safety requirements. They are not only related to magnets, but to other system components, and they range from static magnetic field to dynamic field to pulsed RF field, acoustic noise, cryogenics, and so on. Anyway, people are always concerned about unknown effects of electromagnetic field. Just one of the effects, force on a magnetic object near MRI may be 100 times of its weight. If magnetic object is not properly secured, it will fly towards the magnet bore with potentially fatal effect. So please, no magnetic objects in the scan room. Now, patient comfort and compactness. Early MRI magnets were used mainly for brain imaging, and they had about 55 to 60 centimeters patient bore and used about 2.5 meters long magnets. In early 1990s, Philips introduced a short magnet designs, which is magnet length was reduced to about 160 centimeters, and 60 centimeter bore became a new standard. However, there were demands for better access, including potential for image-guided resolutions. So, in mid-2000s, Siemens introduced a new configuration, wide bore, 70 centimeters diameter. Initially, such systems suffer from a compromise in image quality because uniformity zone in this magnet was pretty short, which required, increased scan time, reduced throughput, and somewhere affected patient comfort. Now, what became commercial? Economy 60 centimeter bore and premium 70 centimeter bore systems available from practically all vendors. There is no performance compromise in terms of uniformity zone, field decay. These systems are identical. 60 and 70 centimeter bore systems are practically identical. And the wide bore is available for 1.5 Tesla and 3 Tesla scanners. Let me skip this slide and go to refrigeration. This table shows a progress in cryogenic technology. Early MRI systems used nitrogen refrigeration in addition to helium refrigeration. You needed to refill helium once a week. And the mean time between helium refill was about 4 months. In 1990s, refrigeration using Jeffrey McMahon cryocoolers was introduced. Which is a cryocooler? It's essentially a cryogenic refrigerator. So the time between helium refills was initially increased to 1 year and then to 4 years. In early 2000, General Electric introduced zero boil off, or better to say zero helium loss refrigeration, that typically does not require helium refill at all. So the system stays without refill for at the same facility, which is typically 7 to 8 years without any refill. Another advantage of zero boil off, it allows elimination of a thermal shield and more compact magnet design. Well, you have to pay for it. It's a higher refrigeration cost, higher electric bill cost, and more expensive system. Okay, so conclusion. Commercial MRI magnets had reached maturity. Efficient, well-integrated magnet design, but many opportunities for improvement and growth. Superconducting MRI magnets, the highest performance, competitive life cycle cost, dominate the marketplace, and the largest commercial application of superconductivity. Okay, and if you want to learn more about magnets, I recommend this paper written by my friends Yuri Lvovsky and Wolfgang Staudner. This was just published about novel technologies and configurations of superconducting magnets. And thank you very much to my colleagues in General Electric, academia, vendors, and competitors who all contributed to this presentation. Thank you.
You want to make a quick comment on the liquid helium crisis that is about to happen?
Good question. Helium industry is a very complicated, and to those ones who are interested, I referenced a book written by John Clark and others about helium as a natural resource, published about a year ago, and it answers to some of your questions. What we have in helium industry, it is actually a monopoly. 70% is a heavily regulated industry in the United States. There are only 13 refineries, helium refineries, worldwide. All of them are like monopolistically controlled. And the disruption, let's say, certain number of plants are closed and for maintenance, and we have a shortage of helium, which happened about a year ago. What we expect today, there are multiple regulations, and what we expect that delivery of helium from the United States will go down quite significantly, and the importance of Russian sources and Chinese sources will increase. The impact, cost of helium on the market, it's not how commercial companies buy it, but on the market, growth is about a factor of 3 over the last 10 years. So this is a serious issue. Let me be very careful and say that vendors of MRI magnets are very carefully following development, and we will offer solution.
Our final speaker today is Tom Dixon, who's going to talk on other practical considerations. I've known Tom for a long time, extremely innovative scientist. Truman Brown talked about chemical shifts many years ago. Tom showed us how to essentially simultaneously use the chemical shift to image in separate images fat and water. It's known as the Dixon sequence. And for his many contributions, this year he was honored by the International Society of Magnetic Resonance in Medicine with its highest award, the Gold Medal Award. So I'm looking forward to hearing more about practical considerations, Tom.
Okay, well, this is good for CME credit, so I guess I have to have some formal learning goals here. I wasn't really sure whether I was talking about resolution or relaxation, so I've pushed that to the back if there's time. Those are the rest of the topics. And start with some comments on, okay. Oh, there's a pointer somewhere. Thank you. Attack this with two hands here. All right. I missed the first slide. Okay. Here is a spectrum of polycarbonate, carbon spectrum. This is the molecule, and it's a natural abundance carbon source. So each one of these lines, or clusters of lines, is a single carbon resonance. And the question is, what happens with field strength here? And let's look at these little guys here. This is obviously a pair of lines. There must be some sort of difference in environment that the things have. If we doubled the magnetic field, what would happen here? Well, this is in parts per million. So in hertz, these things would get twice as far apart, and we might be able to resolve them completely. On the other hand, if we had only half the field, well, we might not realize there were two lines here. And what I described is what happens if you have inhomogeneous results here. The line splits. In the homogeneous case, where you have the environment moving back and forth over the same spins, or the spins moving from one environment to the other, the lines would get twice as wide if we doubled the field, so we would have not much we could do about that, except that we could see how long it takes the averaging process. Okay, so that's one of the big three reasons that you want to go to higher field, is to improve resolution. You conceivably could resolve twice as many lines if you had twice the field. Okay, another advantage is high field is sensitivity. If you double the field, you will get 4 times the signal. And the reason for that is illustrated here. The electromotive force, or the signal that you get, is proportional to the amount of flux that goes through your coil, divided by the time it takes from precession to change sign, or change its direction. This guy. And you might ask, we had this before, but you might have not got here yet, how far can this go on? Eventually we're going to line up all the nuclei, and we can't get any more magnetization out of the system than that. Well, we're nowhere near close. And notice that I've chosen to give this Boltzmann factor with no magnetic units. It's the frequency here. The Tesla and amps and meters are your friend if you're designing magnets, but if you're using them, you're probably interested in what happens in your sample, and that's a frequency unit here. At any rate, the answer is the same, that for 64 megahertz, sort of a standard system here, running at room temperature or body temperature, you have a factor of 100,000 that you could gain somehow or another. But we have more to it than just what the signal is. It's true, the signal goes up fourfold, but there's noise present in any resistor, called Johnson noise, in any resistor setup. And that, it's a longer expression than this, but the noise depends on the resistance, and that's the resistance is the only thing up here that varies with the magnetic field. No? There we go. Okay, so if we double the field, we decrease the skin depth in the copper receiver coil by square root of 2. Whoops. And that increases the resistance, since there's a thinner cross-section that you're going through, by square root of 2. And the noise increases by the square root of that, or the fourth root of 2. There we go. So the signal-to-noise ratio, instead of going up by 4, goes up by 3 1/3. Or if you like to look at that at how much faster can you get the job done if you're signal averaging, that's a factor of 11. Well, this is a biological group, so there's another source of loss that's usually going to be more important, and that is, let's just revisit the last calculations. Now, we double B naught, that's going to double the EMF that's actually within the mouse here, or within the subject. And if we double the electromotive force driving eddy currents, the eddy currents themselves will double. And that means that since voltage, or power is voltage times current, that we get 4 times the power if we keep the same current in the, if we double B naught but keep the current the same in the RF coil. And that increases the coil resistance by 4, since if you put 1 amp through it, the power is just the voltage. And so the noise goes up by a factor of 2, and that means the signal-to-noise ratio went up only 2-fold for looking at conductive biological samples. Or if you, again, are looking at the averaging time, you got a 4-fold improvement in that. Okay, well, I hope that people in the back row can hear me here. Yes? Okay, that's good, because I've got my neck turned around facing the other direction to see what I've written. Okay, doubling B naught is a caveat here. Will decrease T2 star conceivably by as much as 2-fold. And if you double the bandwidth to try to get yourself back to the same position, in that case, you cut the signal-to-noise ratio benefit to only square root of 2 from doubling the field. Okay, more caveats. This sensitivity is involved here, but doubling B naught increases the T1, or the time it takes before you can repeat a measurement. And Seymour Koenig and Rod Brown long ago made lots of tables like this where they have different types of tissues and measure their relaxation rate, which is 1 over the T1, versus frequency. Now if you look here out in the range where we generally operate, the fat has the fastest relaxation and therefore is typically the brightest thing in the image. And since it's the brightest thing in the image, it causes more artifacts than other things do. And it'd be fine, well, the fat's the brightest thing in the field, makes the most artifacts. And if we jack the field up, this ratio of the fat signal to the other signals goes up. So the effect of the motional artifacts is going to be generally worse at higher field. Now, there are some exotic ways to polarize nuclei that don't depend on B naught. See, Truman, I think, discussed some of these. There's the simplest one to understand is you have a separate magnet for polarizing than you do for observing. There's this Pasadena effect that has to do with ortho and parahydrogen and the fact that hydrogen has well, it's a way to eliminate the Boltzmann factor here and get much higher polarizations. Microwaves, I think, have already been mentioned. The electron has about 1,000 times the magnetic moment of a proton. If you can couple the electrons to the protons in a creative way, you get rid of the Boltzmann need. And here's an example of one of those helium or xenon. This one happens to be a helium image of mouse lungs from Duke University. Now, what these four things have in common is that they're not relying on the Boltzmann effect to generate the polarization. So let's revisit this. The EMF depends on flux, which doesn't change, and it also depends on the time to reverse, and that still goes down by a factor of 2. So we double the main field in this case, in these four cases. You double the signal and you double the noise, and the whole thing is a wash. Well, sort of. But if you double the main field, well, in the case of these gases, I think you're almost certain to reduce the T2 star, and that invites changes in bandwidth that actually raise the noise up to square root of 2 times. So the signal-to-noise ratio may get worse by a factor of square root of 2. Here's a case where we expect the low field to outperform the high field. But you can only go so far because the copper losses will keep you from going to zero field, for example. And you also probably want to make proton images with the same apparatus, and you need a field to be able to see those. So we can only go so low. Well, the third main advantage of a higher field magnet is the prestige that it gives you. That's still fully functional. I'm not going to argue with that. And I just kicked in another one here that if it's not good enough to have the highest field, superconducting receiving coils or cold copper receiving coils are another way to gain prestige, and they may be very useful at high fields and small samples. Basically, they're useful where your loss is from the copper rather than from eddy currents within the subject. Okay, on my assignment list, I was supposed to talk about susceptibility too. It interferes with or contributes to almost everything we do, and I'll have a different take on some of these. We've already heard some. It does some good things and some not so good things. Here's one of the most important good ones. This Ogawa discovered, I guess, rather than invented, functional brain imaging, and just by, I assume this is I think this is a mouse, and depending on what he's thinking about, the signal from the brain, from part of the brain, can vary by plus or minus 1 part in 14. That's become a whole industry. Here, Mark Hakey's group has used susceptibility creatively, and the field gradients are high around brain veins, and he's set this up to accentuate the veins in the brain. Here, the most recent ISMRM gold medal went to Chen Ho, and his group has been able to detect single mammalian cells. And these are T cells. They're not ostrich eggs or single cells like that. And we made an attempt at looking at lots of susceptible contrast agent, iron oxide. This is a rat leg that's been injected with 3 micrograms of iron oxide. And you can see that where the iron oxide is here, but you can't make any measurements there. There's dark and there's darker than dark. What are you going to do to quantitate this? And we looked at fitting the phase in the region outside the area where you could get good signals. And we got, instead of 3, we got 2.9 micrograms. And in these control regions, we got slightly negative numbers that are much smaller than 3 micrograms. So this looks good. Well, that's about all I had that I could say that was good about susceptibility for our business. This came up in the earlier talks too. With heavier elements like nitrogen, oxygen, fluorine, and especially xenon's very sensitive. the chemical shift difference between two different compounds is generally large compared to the susceptibility of tissue. So you can do selective excitation of what you want or selective suppression, and that works fine. If you want to do that for protons with water and fat, that doesn't work. I mean, there are claims to the contrary, but there's a cottage industry that's been going on for decades now. The problem is that the air and the water have the susceptibility difference that's about the same as the chemical shift difference. So people have used phase creatively, and this is decades after imaging started, after proton imaging started, and they're comparing two exotic methods here. And if you look where the arrows are, you can see that this is supposed to be water, this is supposed to be fat, and they get it wrong at a couple of spots there. So that's, and here's a worse example that shows what happens, the ugly. These are titanium dots that are used in some sort of orthopedic application. And you can see that there's gross distortion near these titanium things with the standard 1.5 Tesla imager. This is the method where you use a low field magnet for imaging. And instead of this 64 megahertz, this is 2 megahertz, and the distortions aren't so bad. Over here is no titanium. Well, there's titanium in somebody's wrist. And what do we have here? Let's see, this is two different views of the wrist. And with 1.5 Tesla, you not only get so much distortion, there's no possibility of backing out of this because the signal is just gone. But at the low field end here, with a separate polarization mechanism, you can see what's going on. But I don't know why they don't just use X-rays. Okay, I was assigned to talk on facilities, and I don't know much about facilities, so I thought I'd ask a riddle here. How many spectroscopists does it take to watch a worker replace an incandescent tungsten bulb over a magnet? Well, the answer is that LEDs outlast whole MRI facilities, so we're not going to have to watch that anymore. And facility construction has been getting easier as time goes on. Some of us remember when you had to keep the cathode ray tube, when it was color, outside the 3 Gauss line, not even the 5 Gauss line. Well, liquid crystals aren't affected by this. It's the other parts of the magnet. Okay, safety. Well, there are a number of issues here. These things are loud, over 100 decibels in them. That's bad for your hearing. There are missile effects. Subject heating is more of an issue here now that we're going to higher fields. In the way of safety, the lab in Colorado State used to put cushions around their magnets. I don't know if they still do or not. These were 6 inches or so of foam rubber with a nice colorful canvas cover on them. And I'm going to show a movie that'll show you why or how that could be useful. And let's see this hand. Okay, so main field, I want to go over the subject heating before I show any entertainment. If we double B naught, the mouse eddy currents go up and the EMF goes up. So we quadruple power with the same current in the coil here. But I'm not sure that quadruples the heating. I'm not sure that using the same RF current in the coil is going to do. Well, let's see, double. Oh, an interesting thing is it costs you 4 times the heat if you double the signal-to-noise ratio by increasing the field, or if you do it by using the same field and signal averaging 4 times. There's a unity there. But using the same current at high field and low field, that may not be the way to go, because if you're limited in time, the duration of your RF pulse is limited in time by the T2 star, then you're actually going to have to get the job done faster at high field. And so you may more than quadruple the energy deposited if that's the case. Okay, this thing, I had a couple of things I was going to say before the sound takes over, but I didn't give a cue for myself as to what they were. And here's another movie that you...
The explosion captured exclusively by Delmarva 47 News left the parking lot of PRMC and the surrounding area filled with tin and aluminum debris. The hospital spokesman says the blast caused no environmental damage and the mess will eventually be cleaned up.
For some unknown reason at this point in time, the pressure inside the magnet built up and a surge of pressure released from the center of the magnet, causing this insulation to come out of the magnet and over our parking lot. And luckily no one was injured, no property damage at this point.
The unit was 8 years old and was on its way back to the manufacturer, which it planned to resell it. Now here's another look at what happened to it in slow motion.
Yeah. Okay, well that's all I had to show. If there are any comments or questions. All right.